Okay, developing the interval or estimation interval, in fact, stems from our understanding from the probability in the normal distribution. All right, so for example, let's take Z, which is our unit normal distribution. We know that, okay, here we go, this is Z, this is Z curve if you want. Sorry about this, let me just take out this one. I don't know why it happens all the time. Okay, so that's the very ugly curve, but it's okay now. So what do we know about Z? We know that the curve, like any other normal curve, is symmetric with respect to the mean. And if I have here, remember this notation, Z alpha over 2 or ZA, remember we said that. What's ZA? It's a Z value such that the area on the right hand side is A. So Z alpha over 2 is a Z value such that this area here, okay, is what? It's alpha over 2. And minus Z alpha over 2, it's here, minus Z alpha over 2. Also, the area here is equal to alpha over 2. So what can I say about that? That means the probability that Z is between these two values, this minus Z and plus D, all right, which is this area, it's equal to 1 minus these two small areas. And when these two small areas, each one is alpha over 2, that means their sum is alpha. That means this area here is what? It's 1 minus alpha. And this is what we are writing. And you will be surprised to see that such a basic probability statement would lead us to be able to develop a estimation interval. So just an example of that. So for example, Z 0.025, what that means? That means this area here, it's 0, so it's 2.5%. Okay, this is 2.5%, which is the area on the right hand side also here, it's 2.5%. So which means what's left in between? Okay, both of them are 5%, so what left is 95%. So here we go. This is what we're writing here. All right. So, and we have learned also in the sampling distribution that X bar is a variable that follows a normal distribution. And which means what? Which means, as I can do with any variable that has a normal distribution, I can standardize this variable. So I can standardize X bar. And this is what we were doing to find the probability in a sampling distribution, right? So this relationship between Z and X bar, it applies like it applies for any with any relationship between Z and any variable X. So X bar is my variable's normal distribution, and this relationship exists always. This is how I standardize, okay, where mu is the sampling distribution mean, and whatever you see here in the denominator, this is the standard deviation of sampling distribution, which is what? Which is the population standard deviation divided by the square root of the sample size. We have learned that before, but I'm going to now use this one, okay, to replace Z in the above probability statement. All right, so what I'm going to do now is I'm going to use the probability statement that I showed you in the previous slide, and I'm going to replace Z with its equivalent in X bar, right? Because we wrote that Z is equal to X bar minus mu over square root of n. So here we go, I replaced it here. And these values are fixed values, right? I read them from the Z table. Like, for example, if we said that if alpha over 2 is 2.5%, that means I know that Z value, right? It will be 1.645, and this will be minus 1.645. So this is a value. All right, so now what I can do next, look at this. It's very logical development of this probability statement. Now what I'm going to do, I'm going to get rid of the denominator here in the middle element. Okay, so I multiply this and that by sigma of a square root of n. So I will get this. Okay, I just multiplied every element every part of the probability statement by sigma of square root of n. So here it will cancel out, so I don't have now any more denominator, and here the same, I have it here. Okay, so and still everything, the probability is 1 minus alpha. So you can guess now what was going to be my next step. I'm going to get rid of this mu. So by adding mu to the three terms also. So here we go. I added the mu here, I added the mu here, so mu and minus mu, it will cancel out, and I added the mu here. So here what I'm saying now, I have a probability now. I changed my probability from the z term into an x bar term. And in fact, this is not what my final objective. But this developing the probability statement from the z, which was easy for us to start with, and to get it into this form, I think it was fairly easy, right, for you to understand. So, but this is not where I'm going to stop. I'm going to assume that you understood that, and you're going to trust me that we can do exactly the same algebraic development and replace the middle part, or have a probability statement with the middle part with the mu except or instead of x bar. All right, so hopefully you have understood very well what we did so far, and as I told you, doing exactly the same kind of algebraic manipulation, you will end up with a probability statement where I have mu in the middle. And you can guess why I want this, not x bar in the middle, because we want to find an interval for mu, not for x bar. Okay, so look at this. Here we are saying that the probability that mu is, or x bar minus a certain value less than mu less than x bar plus a certain value is 1 minus alpha. So what are we saying is this? X bar, you know that we get it by selecting a sample from the population. And when we talk about probability, we always infer a long-term or a very large number of selections and trials. Okay, so what we are saying that with repeated sampling from the population, you will always get an X bar such that every time when you subtract that value and you add that value here, you will have in a lower level, okay, and an upper level where certainly mu will be between these lower level and upper level. And you have a confidence, okay, of 1 minus alpha. Why? Because this will happen, the probability that this will happen is 1 minus alpha. So you will have such a confidence that this will be an interval that will contain your mu. So we have just developed a method or our confidence interval that can estimate the population mean. Okay, and here we go. This is our interval estimator. Okay, where we say that this one is my lower level. Okay, and this one is an upper level, right? Because what's an interval? An interval, something like that, for example, 2, 5. Okay, this is an interval that has a lower level of 2 and upper level of 5, and it has all these values in between. Okay, now let's have some formal definitions of some terms. What do we mean by 1 minus alpha that we used previously, which was the probability, right? We call that the confidence level. So, for example, I'm 95% confident that this interval, for example, this one, contains a certain parameter. Okay, and as I mentioned that now many times, you can see that this part here, okay, which I'm repeating it here, we call that the lower confidence level. So LCL or simply LL. Okay, and the other one, which is the opposite, it's X bar plus Z times sigma of square root of n, we call it the upper confidence level, so UCL. Okay, now very often we will be denoting, and in fact most of the times we're going to denote our confidence interval as x bar, which is the starting value that we read from the sample. So it's equal to x bar plus or minus z alpha over 2 times sigma over square root of n. All right, and you can see here, so x bar plus, this will give me my lower level, and x bar minus will get me the lower level. Okay, so this is a very nice concise way to represent the confidence